show that the relation R in set 1, 2, 3 given by R equal to 1, 2 and 2, 1 is symmetric but neither reflexive nor transitive. So it is a simple sum because R is already given in roster form. The elements of R are 1, 2 and 2, 1 consisting of only 2 elements. Let me first of all check it is symmetric. You know 1 is related to 2 and implies 2 related to 1. 1, 2 and 2, 1 both the elements are present there and there is no third element. So if 1 is related to 2 implies 2 related to 1, hence R is symmetric. It is confirmed it is symmetric. Now the second part, first part we proved that R is symmetric. Now let us check in the second part if R is reflexive or not. Okay. So what is reflexive property? That each element should be related to itself. Let me check the first one, 1. Is 1 related to 1 means 1, 1 belongs to R? No, 1, 1 does not belong to R. So I need not to check the others. So I can conclude that R is not reflexive. Is not reflexive. Now let me also check if R is transitive. See here 1, 2 and 2, 1 belong to R. That means 1 is related to 2 and 2 is related to 1. For transitive, for the function to be transitive, it should imply that 1 related to 1 or 1, 1 belong to 1 related to 1. That means 1, 1 should be there in the relation, but 1, 1 does not belong in the relation. So we should conclude that R is not transitive. So it means we have proved that R is symmetric but neither reflexive nor transitive. Now the next sum is, you are given a set A, a set of books in the library, and given by R equal to XY such that X and Y have the same number of pages and we have to prove it is an equivalence relation. It is a very simple question of the kind equal to, like equal to instead of real numbers. It is a similar situation. Let's see one by one. For equivalence relation, what all you need to prove? We need to prove that number 1, the relation R is reflexive. That means every element X is related to X. What does it mean? That if X denotes the number of pages in a particular book, then the number of pages will remain the same as that particular book has. So every element X is related to X for all X belong to A. So you can conclude that yes, R is reflexive. Number 2, R is symmetric. For that we need to prove that if X is related to Y, then Y is related to X. It is obviously there because if X is related to Y, that means the number of pages in X is same as the number of pages in Y. Or in other words, number of pages in book Y is same as number of pages in book X. So that means Y is related to X. So X related to Y implies Y related to X. So clearly the given relation R is symmetric. And now let us verify third that R is transitive. Let X is related to Y means the number of pages in book X is equal to number of pages in Y. And Y is related to Z. That means number of pages in Y is same as the number of pages in Z. Now what does the first two relation imply? First two statement, number of pages of X is equal to Y and number of pages of Y equal to Z. So can we conclude that number of pages in book X is same as the number of pages in book Z? So that means X is related to Z. That is, whenever X is related to Y, X is related to Y and Y is related to Z implies X is related to Z. So we conclude that R is transitive. And finally we may say, because the function R is satisfy all the three properties, reflexive, symmetric and transitive, so R is an equivalence relation on the given set A of books. Library. Show that the relation R in set A consisting of numbers 1, 2, 3, 4, 5 given by R the relation equal to AB such that A minus B is even. Modulus A minus B is even. Is an equivalence relation. Such that all the elements of 1, 2, 3 are related to each other and the elements of the set 2, 4 are related to other. But no element of 1, 2, 3 is related to any element of 2, 4. Okay. So this is a kind of sum we have already done in the introduction part in example 4 and 4 dash. But I'll do it for you. Okay. So given is a set A equal to 1, 2, 3, 4, 5 and the relation is AB, A related to B such that modulus A minus B is even or divisible by 2. So let us first prove that is an equivalence relation on it. Number 1, reflexive. You take any number, say A, so we can claim A is related to A because modulus of A minus A is obviously 0 is even or divisible by 2. So whether it is 1, 1 or 2, 2 or 3, 3, so in general 1, 1, that is for all A belong to the given set capital. So we can conclude that yes, the given relation R is reflexive. Now to check symmetric. Let A is related to B for the given set. That means modulus of A minus B is even. I may take an example. For example, if I choose two numbers, say 1 and 5. So modulus of 1 minus 5 will be what? 4. Modulus of 1 minus 5 minus 4. Modulus 4 is even. Okay. So A minus B is even. Implies modulus of, take minus sign common inside, minus of B minus A is even. And modulus of minus B minus A is same as modulus of B minus A. So modulus of B minus A is also even. So clearly it means that B is related to A. If you look at the particular example, 1 minus 5 modulus is 4. And what about modulus of 5 minus 1? That is also clearly 4. That is even. So we can conclude that if A is related to B, then B is related to A, or in other words, R is symmetric on the given set A. Now to check the third required condition, that R is transitive. Let A is related to B, that means modulus of A minus B, modulus A minus B is even. That implies A minus B is somewhat of kind 2k, where k may be any integer, say z. Why? Because k can be plus minus 1, 2, 3 kind, even. So if A minus B is 2k, that is one relation. And similarly, also let us say, because we are checking transitive property. So A related to B and let B is related to C. So likewise we can conclude that B minus C is also even equal to say 2J. Okay. So now what about A minus B plus B minus C equal to 2K plus 2J. If I take K common, then it is twice K plus J. And out here A minus B plus B minus C gives you A minus C equal to twice K plus J. Obviously K plus J will be integer if K and J are separately integers. So what does it mean? That A minus C is even, and obviously modulus of A minus C is even, or A is related to C, and hence as A related to B and B related to C implies A related to C, so we can say R is transitive on A. So now let us conclude that as R is reflexive, symmetric and transitive, so R is an equivalence relation on A. So that is one part of it, that R is equivalence relation on A. Now further we have to prove that A is divided into two equivalence classes, though in the sum he is not using the term equivalence classes, but if I say that he is saying that all the elements of the set 1, 3, 5. Now consider, let me call it a set B. 1, 3, 5 are related to each other. It is very easy to check that. You take any two elements A and B from this set, say B. What do you find? 1 minus 3 modulus is even. Clearly 3 minus 5 or 5 minus 3 is even. So we can conclude that any two elements are related. Likewise, you take the other set, say we may call it C, consisting of 2, 4. Then obviously 2 is related to 4, as modulus of 2 minus 4 or 4 minus 2 is 2 is also even. So we conclude that all the elements of the set 1, 3, 5 and that of 2, 4 separately they are related to each other. But what if I take an element, say 1 belongs to B and let me take an element say 2, or better you take 4 belong to B. Check whether 1 is related to 4 or not. 1 related to 4 would mean that 1 minus 4 modulus, that is 3, is even, which is wrong. Which is wrong. Does not exist. So we say 1 is not related to 4. So what do you conclude? That all the elements of set B, say 1, 3, 5 are related to each other. That of C, that is 2, 4 related to each other. But if we take an element from set B, another from C, they are not related. So we can, that's what we have to prove. But may I conclude one further steps, that 1, 3, 5 and 2, 4, what is their union? The given set A. And what is their intersection? Null set. So we can say that the given relation divide the set A into two equivalence classes B and C.